Thank you. So yeah, I'm Leo. I work with the Codex team. We are a team that is specialized on decentralized storage. And this work was done in collaboration with my colleagues, Shava and Dimitri, who are sitting in the public. So thanks to them. But I also want to thank Jesse, Eric, Ben, Mark, and all the other members of the Codex team for so many discussions that help in this research. And I also want to thank the Ethereum Foundation because of their trust and so many discussions in this collaboration that we are doing with them. So today I'm going to talk about Ethereum scaling, about the structure for data availability sampling, the model input, the data that we have gathered from the Ethereum network, and also the simulator that we are building, and then I will finally conclude. So we want to scale Ethereum. So if you think about Ethereum like a small computer in the old 90s, we want to transform that into a supercomputer. Now, when we talk about performance in blockchain technology, we talk about number of transactions per second. So today, we do about 15 transactions per second, and we want to scale to something in the order of tens of thousands of transactions per second in the future. Now, to do that, we are focusing on a rollup-centric approach that has been already presented in the last few days. But the thing is that rollups needs data where they have to, put their information. And so for that, we need to increase the block size. And so today, if we look at the average block size for the Ethereum blocks, it's about 100 kilobytes. And we want to increase that to something in the order of maybe to 32 megabytes. All right? Now, the problem is we don't want all the networks in the Ethereum network to be supercomputers to be able to handle so much data. So in order to solve this, we have to do sharding. More specifically, data sharding, okay? And then when you are doing data sharding, basically you are taking your block and you are distributing that block in different chunks, and you are sending the chunks to different validators in the network, but nobody in the network has the entire block. Now, and that is a risk because then if some nodes go offline, then you might lose some of the data. And then that forces you to do what is called data availability sampling. Now, there are several recipes for data availability sampling. We focus on this one, that is the one that I'm going to present today. So you need 2 cups of erasure coding, better if it's Reed-Solomon encoding, a tablespoon of KCG commitments, and a lot of sampling. Now, there are a lot of recipes for data availability sampling out there. I'm not saying that this is the only one, perhaps even not the best one, but this is the one that we are exploring right now, and that might change in the future. Now, what you want to do is you take your block, you divide your block in different chunks, and then you erasure code that. And then you have some extra data that you can use in order to repair your block if something goes down. So if you lose 2 chunks, for example, you can repair it. If you lose up to 4 chunks in this particular example, you can repair it, and then you can recover all the data. Now, this is not enough, because it could be the case that the block proposer actually distributes the data, but it also distributes parity data that is not really parity data, but only garbage data. And then you will not be able to recover in case of failures. So to solve that, we use what we call KCG commitments, and is basically a proof that says that the chunk of data that you are getting is part of the polynomial of the Reed-Solomon equation that you solve in order to do the encoding. And this is a small proof that guarantees you that the piece of data that you are getting is actually something meaningful, and that you can use that in order to recover data when data is missing. Now, you can do that in a 2-dimensional structure. And so basically, you use your block data, you put it in the blue squares that you see there, and then you erasure code all the rows, and then you get this kind of structure. But you can also do that with all the columns. And then you can also repeat that with all the rows and columns that you have encoded, and you end up with a structure like this. Now, to give you some numbers of how the structure for DAS looks like today, basically you have samples or chunks that are in the order of 512 bytes. And to that, you're going to add about 48 bytes for the KCG commitments. And then the original data is the blue part of the block, and then the red part is what you generated with the erasure codings. And so what you want to do here, so in this particular example, we are working with blocks of 512 columns and 512 rows. And then that gives you a super block that is more or less of the size of 140 megabytes. OK. So when you are looking at block availability, like, for example, if you have only the original data, you can erase code that horizontally, and then you generate that part, and then use the rest to encode vertically, and then you generate the whole structure. Now, let's imagine that you distribute the block over the network, and a bunch of nodes go offline, and you end up with a structure like this on the left side. So you still have enough 50% of the blocks, of the chunks, in the left side to generate the rows. And then once you have all the rows being regenerated, you can use that to regenerate the columns, and then you have reproduced the whole structure again. But now let's look at an example that is not possible to reconstruct. Here you have 3 rows that are entirely correct, 3 columns that are entirely correct, and the rest of the data has disappeared over the network. In this case, you cannot reconstruct any other row or any other column, and then you have lost too much data, and then basically here you can say that the block is not available. Okay? So in this case, we don't want validators to attest for this block. All right. Now that is about the structure of DAS. Now let's talk about what happens after you generate the structure. So the block builder sends this block to the network, but how does it do it? It has to disseminate rows and columns to different validators. So each validator in the network will get a specific number of rows and columns. Could be 2, could be 4, could be 8. We are playing with those parameters. After that, you populate a DHT with all the samples of the block, and then you do sampling to check that the chunks are actually where they are supposed to be. If you find all the data that you ask for, that means that the data is available, and you can attest for that block. But in the presentation today, I'm going to just focus on the dissemination of rows and columns to the validators, which is the first part of the simulator that we are building. Now, as I said, you have this block builder that is connected to the network and is connected to many beacon nodes. And so you may be connected to a validator that is behind a beacon node, but there are also beacon nodes that have multiple validators, and then they will have to access multiple rows and multiple columns, depending on the number of validators that they have behind. Now let's focus on the data that we know from the Ethereum network today. For that, we use the crawler that we have been developing for a couple of years already. You can access it in the QR code, and there is this public dashboard that we have. So all this data, is not 100% exact vision of the Ethereum network, because crawling a peer-to-peer network doesn't give you an exact figure of it, but it just gives you a good estimate of how the Ethereum network looks today. So you have about 10,000 nodes in the network today, about 40% Lighthouse, 40% Prism. Between 7 and 10% are Nimbus and Teku, and then a few others, Lodestar and a few others. Regarding the number of nodes that are subscribed to attestation networks, we see that about 6,000 are not registered in any attestation network, and there are about 1,000 of them that are registered to 64 attestation networks. These 1,000 nodes most likely are hosting many, many validators, perhaps in the order of hundreds of validators behind one single beacon node. So we can use all this data to put it into our simulator and understand what is happening. We also know that about 55% of the nodes are in a cloud, and about 40% of them are in residential homes. Regarding latency, we also see that the distribution, geographical distribution, is not that great. That was already mentioned in the LATAM talk, which is very interesting. But regarding latency, we see that most of the nodes are located within 100 milliseconds from each other. When you look about the networks, the nodes between them, you will see clusters that form, like in Asia, which is the top left side of the heat map. In the center, you have Europe, and in the bottom, you have America. But most of them are located within 100 to 200 milliseconds. So we can use that to plug that into our simulator. Regarding bandwidth, we also did a study. I'm not going to go too much into the details here, but we have a good estimate about the average, minimum, and maximum bandwidth of the nodes nodes over the network. Now, the simulator. So we are working with a simulator that relies on GossipSop. GossipSop is an efficient and reliable protocol. It uses a graph mesh to push messages. You have nodes that are connected to 6 to 8 nodes. And then you send gossips in order to pull new content. Now here the idea is that you will have one GossipSop channel for every row and column in this large structure that I have presented. So if you look at a structure with 512 rows and columns, then you will end up with about 1,000 GossipSop channels. The simulator is highly configurable. We have a large simulation space. So you can configure the number of nodes, the type of nodes, the number of validators per node, the network degree, the failure rate, and so on and so forth. We also have other parameters, like if we want to make the simulations deterministic, if you want to plot all the results, and so on. So if you want to access the simulator, you can scan the QR code, and you can play with it. Now, just to say, this is a work in progress. We started working on this a few months ago. So if there is something that doesn't work perfectly, feel free to contact us. We'll be super happy to help you and to work with you. Now, just to give an example of the configuration file, I'm not going to go through all the details here. But yeah, just to explain, you can parameterize the number of nodes in the network. You can also say what are the type of nodes that you want to see in the network. So for example, you have two types of nodes. You have the solo stakers that are small nodes in houses that have perhaps a small bandwidth and that only host 1 or 2 validators. And then you have like the really large nodes that are probably staking pools that they have maybe hundreds of validators, great internet bandwidth, and great hardware resources. And then you can also configure how many validators you want to set in, behind each one of those nodes. Oops. You can also configure the block size. So this is to parameterize how much data you want to put inside a block. You can also play with the number of rows and columns that you want to send to each validator. This is an important parameter for data availability sampling, because the more rows and columns that you send, you have more reliability, you have more redundancy in the system, but you are also consuming more bandwidth. And so there is a trade-off there. There is a sweet spot to be found. We can also configure the latency of the network. We can also configure the sample size. And we can also configure the bandwidth. And actually, you can configure different bandwidth for different types of nodes in the network. Now, after you launch the simulations, as I explained, you have a combinatorial space with many, many dimensions. And then when you launch the simulator, you will explore all these possible combinations that you set up in the configuration file. And then you will get results for each one of those simulations. And then I will explain here just a few examples of what the results look like and what are we doing with those. So on the right side, you see the number of validators that get assigned to a specific row or column. Okay? So in this particular simulation, we launched 7,000 nodes. And with the configuration of validators per node that give us something in the order of 530,000 validators, which is relatively close to what we see today in reality in the Bitcoin chain. And we set up the block size to be 512. So it's normal that the x-axis that you see here goes until 512, because you only have 512 rows and columns. And then you see how many validators are receiving those rows and columns. Now, on the left side, right side for you, you have the progress of how many samples are received from the beginning of the simulation until the end of the simulation. Please know that the x-axis is milliseconds, and it goes up to 600 milliseconds. So it's a little bit more than half a second to distribute one block over the network. It goes from 0 to 100%. The blue line is the number of validators that have received all the samples that they have to receive. And please notice there is a big spike. And then the green line is the number of nodes that have received all the samples that they have to receive. Now you might be wondering why the blue line is not the same as the green line, because validators are in nodes. The reason is because the blue line just says when the validators receive it. In the green line, you only count as ready when all the validators inside the node have received all the samples. Okay? So even if you have 500 validators, you might have received 499 validators, all the samples, but maybe one validator still didn't receive all the data that it was supposed to receive. So you will see this delay of about 50 milliseconds or so. Now, when we look at the network, in this particular simulation, we are using 5 gigabits per second for the staking pools and 50 megabits per second for the solo stakers. Now, please don't take this number as the ground truth. This is just an example of a simulation that we used. And you can see that this is exactly what we see. We monitor how much data is sent and received over the network. On the left side, you see the send data, and on the right side, the receive data. And you can see that, yeah, we are using the bandwidth at the maximum in order to distribute all the rows and columns that we are supposed to distribute. For the solo stakers, which is the light blue cyan line in the bottom, we see that we don't pass the bandwidth that it was written in the configuration file. Now, all this is nice, but then what else can we do with this simulator? So one thing that we can do is try to explore the breaking point. Okay? How much failure rate I can accept in my system until the block is not available anymore. So here is an example of that. On the left side, you see the same simulation I just presented, in which the red line goes to 100%, meaning that the block became available and everybody received the samples that they were supposed to receive. On the right side, you see a simulation where the blue line and the green line are non-existent because the validators didn't receive the data that they were supposed to receive. And this is because I increased the failure rate up to 80%. And then what happens is that we send some samples. Some validators try to reconstruct some of the rows and columns using Reed-Solomon encoding, but they don't manage to reconstruct everything, and the whole thing stagnates at 35%, where there is no more samples that can be reconstructed in any direction, and then nobody sends anything anymore. And then at that point, we are not making any progress, and the block is unavailable. Okay? Now, another thing that we can do is to say, well, instead of sending the whole row or the whole column, maybe you can send only the original data and let the validators recreate the erasure-coded data by calculating the Reed-Solomon encoding themselves. In that way, you save 50% of bandwidth, because you only have to send 50% of the data, and then maybe the simulation will be faster. And this is what we see exactly. If you notice, when we send the whole row and columns, the simulation finished, the block distribution finished at 600 milliseconds. If we only send half of it, then we finish at 400 milliseconds. So that's an improvement of 33% in time to availability for the block. Okay? So this is just to give you a few examples of the things that we are doing with this simulator. There are many more. And so if you're interested, again, please check out the repository and feel free to contact us. So in conclusion, there are many recipes to building data availability sampling. We are exploring this one, but we are not close-minded. We are leaving the space open. There are many changes that can come in the future. We are building the simulator to study all those different parameters and to find the best combination to implement data availability sampling for the scalability of Ethereum. And we are also measuring the Ethereum network in real time so that we can plug all this real data into the simulator and get the best possible solution for scaling for Ethereum. Finally, I want to say that our team at Codex is working on long-term storage, which is also an important problem for Ethereum. And so if you're interested in that, please come to talk to us. Thank you very much.